Alright, welcome back to another shear and moment diagram example. In this example, we're actually going to look at this simply supported beam, has a point load in the middle, and we're actually going to use the equation approach to come up with equations for these spans to draw our shear and moment diagrams. Now, when you're using the equation approach to come up with equations between these spans to draw shear and moment diagrams, it's best to use equations for spans that have either constant or simple loading or no loading at all. So for an example, in this scenario where we have a simply supported beam and a point load in the middle, I would not advise to come up with one equation that illustrates and depicts the shears and moments for this entire span. Instead, I would try to break this up. So maybe between this pin and this point load, we can come up with one equation because there's really no loading between the pin and this first point load. And then maybe we can come up with another equation from this point load to this roller support. So now we have two different equations, and we can use those equations to come up with the shears and the moments for this beam. So I'm going to go ahead and label this point A, point B, and point C, and we're going to come up with equations for two spans. Span 1, which goes from A to B, and span 2, which goes from B to C. So with any shear and moment diagram that we want to create, we want to start off with the free body diagram first. So I'm going to go ahead and draw this free body diagram right here. I have this point load in the middle, so that point load is going to be P, and then I'm going to have a reaction at A and a reaction at C. Well, what are those reactions? We have a point load P, which is 5 kips, and this total length is 6 feet. And this is L over 2 and L over 2, so this is 3 feet here, 3 feet here, so I'm going to draw that here and here. And since this is simply supported with only a point load in the middle, we can obviously see that the reaction is going to be 2.5 kips on both of these ends. So at A it's 2.5 and at C it's 2.5. And our points are A, B, and C. So the next thing we're going to do is we're going to go ahead and start constructing our shear diagram. So this is shear and the units are going to be in kips. And what I'm going to do is I'm actually going to look at this first span here, and I'm going to try to come up with an equation that represents the internal shears between points A and B. So I'm just going to write here first span, which is that span that we just looked at, this one here. And I'm going to take a cut anywhere between that span. It doesn't really matter where, so long as that cut is in between point A and point B, in between the span. If I go ahead and draw that diagram here, I have point A here. I have this reaction of 2.5 kips, and then I have this cut somewhere along point or span AB. And so what I'm actually going to do is I'm going to say the datum is here at point A, and any point along this span between A and B is just a distance x from A. And what this is going to allow us to do is to come up with shear and moment equations in terms of x. So in other words, we would have equations that have a variable x, and we can plug in x or a distance and figure out what the shear and moment diagrams or values are at a distance x from A. So if I go ahead and draw our positive shear sign convention here on the right side of this cut, and I'm just going to say this is V of x, so this shear is going to be a function of x. Then what I can do is I can sum the forces in the y direction equal to 0, and I can see that I have a positive 2.5 kips there, and then this Vx is minus V of x is equal to 0. And now what I can do is I can add V of x to both sides, so V of x is equal to 2.5 kips. So you'll notice that on the right side of this equation there is no x, and that means that the shear between points A and B is a constant. It's just 2.5 kips. So I can go ahead and draw this 2.5 kips all the way to B. That should be a straight line. And we know anywhere along this shear diagram, the shear is 2.5 kips. So I'm going to go ahead and scroll down just a little bit so we can make some room. And now what I'm going to do is I'm going to look at this second span here. So from B to C. So I'm going to write second span, and I'm going to go ahead and draw that second span. I'm just going to take a cut, some random cut between B and C. It doesn't matter where it is because we're going to write it in terms of x. So we have point A here. Again, we have this 2.5 kips here, and then somewhere here is point B, and we have this point load 5 kips, and then we have our cut, and I'm going to go ahead and draw our positive internal shear, and I'm going to label that V of X. We know that the distance between A and B is 3 feet, so from point B and beyond, we're going to take B as a datum and say any distance from B to the right hand side is just a distance X from B. Now the reason I shifted this datum from point A in the first span to point B in the second span was because I really don't have any loads between point B and C, and I didn't want to interrupt the shear equation with other point loads that happen at certain distances of X from point A. So it's easier just to have this datum at point B and come up with an equation that represents the shear diagram just between points B and C. And that's because we already have an equation that represents the shear between points A and B, or the first span. So let's go ahead and do that. Let's sum our forces in the y direction and set that equal to 0. Here we have a positive 2.5 kips, and then we have a minus 5 kips, right, because it's going down. And then I have this minus V of X, and that's equal to 0. So 2.5 minus 5 is negative 2.5 kips, minus V of X is equal to 0, and then I can add V of X to both sides, and I get V of X is equal to negative 2.5 kips. And again, we see that this is a constant shear because there is no X on the right hand side of this equation. So we know that the shear is a negative 2.5, and that's constant along points between point B and C. So we have positive shear here, and we have negative shear here. So this is 0, this is 0, and we have negative 2.5 at every single point along the shear diagram between points B and C. So cool, we have our shear diagram, and we used an equation approach to figure out what the internal shears are between each of these spans, between A and B and C. In the next part, we're actually going to look at the moment diagram, and we're going to do the same approach, but now we're going to use the moment equations, the internal moment equations, to figure out what our moment diagram is for this structure. So see you then.